Actually, it's going to be easier for me too. I've been struggling with Greek yesterday, and well, 2 days ago. It wasn't too obvious, but Ramesh is a lifesaver now. Now, many of the terms, especially for the power grid, I don't know the corresponding Greek terms. I should, but I don't. Anyway, welcome. Good evening, or good morning for whoever woke up. This is going to be the second module in the school. We're discussing about critical infrastructure security. And I'll take, yesterday I took precedence trying to understand who was in the room. I'll do that at the end of the lecture. And then we'll assign teams for the assignments. And we'll discuss more about what the assignments will be. But that's for the people who registered and want to get a certification of attendance. The rest, you don't have to do anything. Just attend or sleep or whatever you feel like doing. This room is much bigger, and it doesn't really help with interaction, but just treat it like we're 2 days ago, like a much closer setting. If you're going to interrupt me anytime, raise your hand. I can probably hear you, right? Ramesh, say something. Yeah. OK, perfect. So it has proper acoustics. So just interrupt. I'll be asking questions, too. I want to have a discussion like I did 2 days ago and not be like a podium speaker that you have to listen to and fall asleep after 5 minutes. I'd like to keep it interactive like the first time. So I'll start, and as I said in my email, I'll do the first half. We'll talk about power grid. If there are any leftover slides, we'll finish them off in the Monday of the following week, not the next week, the week after. Because also, since you expressed interest in hardware security, Ramesh here can give a talk about basics on hardware security and some information maybe about biochips, but it's totally up to you what you want to do. So let me start. And we kind of started the discussion last time by introducing what critical infrastructure actually means. And we spent some time discussing what parts of the country are considered critical infrastructure, and we all came down to the same conclusion that it is every sector, every part of a country that any problem, any effect, any distraction to it can have a tremendous effect in the well-being of a city. So starting from the power itself to the dams, to food and agriculture, communications, critical manufacturing, there's so many parts that are invisible to us and we don't notice. But if something happens to that part, then it can have a very big effect in a city. So in this module, we'll focus on the power grid. And the power grid is something I've been working on. It's been 4 years now. We've been working on, Ramesh and I had a joint project with electricity provider in the US, and then we expanded it with other research projects. I'll discuss a few today. But first, let's try to understand what power grid exactly is. So the typical abstraction people use for the power grid has 4 distinct components. And let me try to find this one. OK. 4 distinct components, namely generation, transmission, distribution, and the actual consumer side. So the first part is generation is actually a big factory where energy is produced. In Greece, we mostly use coal, but other countries are using other forms of energy like nuclear. Even now we're going to renewables, solar panels, wind turbines, and so on. But this is the first part of where the energy is being generated. So generation is the first step. And then once you generate the energy, this has to be transported to the customers, right? Either to the city itself or to parts that the energy needs to go. And the transmission over long distances is called the transmission part of the power grid. So transmission has hundreds of kilovolts. It's typically more than 120 kilovolts that you consider a transmission side, actually more than that. And these are the big poles you see sometimes when you travel in the countryside. They're poles that look much bigger than what you see in a city, right, or close to buildings. So these are transferring electricity in very, very long distances. And that's called transmission. Then, in order to start delivering to the customer, you go to the distribution side. So after transmission, you have distribution, that you have smaller substations that scale down the voltages to lower voltages, and then those substations slowly start connecting either directly to buildings, like a university will just get a high voltage line directly because it's a very high load customer. But if you have a house, you go through a smaller substation, and then you have your smaller wires feeding the actual houses with voltages at around 220 volts in Greece and in Europe. So this is the abstraction, right? 4 components: generation, transmission over long distances, distribution to start giving to the customers, and then the load side where the customers are actually absorbing the electricity. So that's a typical power grid. Yes?
I've heard the US is functioning at 60 hertz instead of 50 hertz as in Europe. Is there any specific reason for this frequency?
So let me clarify, I'm not a power engineer, right? But I've read that the frequency choices among countries are mostly historical. So when they set up the power grid, they made the choice that either 50 or 60 hertz, but nowadays it doesn't make a big difference the way the electricity is produced and transmitted. It doesn't make much difference today. So they do have 50 compared to 60. I think Japan has 1 something, 100 something, has much more than that. So they have made their choices for their own historical reasons, and now they're stuck with it. They cannot change it. So we're focusing on security of the power grid, right? And the question that naturally arises here, it's a question more applicable to the United States, but it's something we'd like to discuss as well, is who's responsible for the security of the grid, right? And that's a big question in the US, because in the United States, the electricity providers are all private. There are more than 3,000 private companies controlling part of the power grid. Here it's only we only have 1 utility controlling everything. And nowadays it still belongs to the government, but it's slowly getting privatized here too. So there's a very big question about who's actually responsible for this. Is it the actual government that has to come and give directions to the utilities? Because essentially, for a utility, if the power goes down, it's just damage to their profits. For a country, if the power goes down, it can be a damage in many other fronts, including all the parts of the critical infrastructure we saw, and things like the country could have a problem in a war setting and so on. So in the US, you have the actual government, you have the utilities here, and you have the actual vendors who are selling the devices to utilities. They is buying devices from Siemens, is buying devices from Allen Bradley. They go after companies and they buy devices to put in their own grid. So you have a 3-party interaction here: the actual government, the utility itself, and again in the US there are more than 3,000 utilities, and the vendors. So it's a kind of an interesting political game, right? Who's responsible for what? A country has a lot to lose, but if you enforce too much on the utilities, then how do you control? Then the utilities care about the profits. If they start losing money because of security constraints and security problems, then they're going to have a problem, right? And then the utilities end up blaming the vendors, because the utilities are just integrating the devices. They buy the device from Siemens, from SCL, from General Electric, and they say, okay, this is what they gave me. It's not my fault. I just took a device. This is it. So go after the vendors if you want to actually have security. So the blame goes down, it's being shifted to the vendors, but the vendors are saying, well, I mean, we give the device, you don't use it properly. If you configure it properly with proper security mechanism, VPN, firewalls, proper DMZ zones, there's so many ways you can properly segregate your network that the vendors at the end don't really have much to say there, right? If you do a very poor job in your security of your network, then it's kind of your problem as well. But it's interesting to see how all this interaction works together. And what we were doing actually in that project I mentioned that we're funding, Ramesh and I were copy-eyes on this. One of the utility companies gave us some of the vendor devices and said, can you find out whether devices are okay? So it's more of trying to proactively understand the security of their own network. And we had a few devices. They said, check the devices. And then they also mentioned, can we come up with some defenses, some way to detect whether there's a cyber attack in the power grid and prevent any further damage. So this is what this project I'm going to describe was about. So in order to be able to accurately assess security of a grid, you have to have a platform to experiment on. You cannot really play in your house. You cannot play in a lab that doesn't really have anything to do with the power grid, right? You have to create an environment where whatever cybersecurity defense you develop can be properly assessed, right? You can't have a device like that's off or it not connected to the network and say, okay, what if I have an attacker? Well, you have to connect it. You have to properly function it in order to be able to have an accurate assessment of what you're actually trying to do.
The vendor device is the device that shares the energy among the customers?
No, vendor, I mean companies like Siemens, General Electric that sell you the box, like the computer, that you put in your system.
So that's how you define the vendor device?
Yes, the device sold by the vendors. The utilities do not have smart devices. They have the transformers, they have the electrical part, they also buy that, but the smart part of it, of the smart grid, or the power grid, comes from outside vendors. Mostly, Siemens has a big chunk, ABB, Schneider Electric, General Electric, many companies, Honeywell. So again, the first step is to, to actually create a testbed. So a testbed means a platform that can help you assess whatever you're trying to assess, right? And typically, in the case of a power grid, what has been typically the case for assessment is optimal power flow. How can I distribute my substations optimally to make sure that if I have some problem in one of the areas, it doesn't really overload my network throughout. But what we want to do as a testbed is to be able to understand if an attack goes through, what happens actually in the grid. So to do that, we have to create a testbed. And essentially, it means that we have to map what this network is actually trying to do, this part, the generation, transmission, distribution, and the end load, to something that is in the room, right, is in the lab. And that's a picture from Brooklyn in New York, and were you there? I should update it because we have a similar setup in Abu Dhabi now. But that was where we first started setting up our testbed, where we're trying to have devices, connect them to some kind of a power generation mechanism, and then through data acquisition, try to understand what the controller is trying to do. And to do that, we have to understand what part of the network we're going after. And the specific part of the network we're after is those devices called reclosers. I don't know if you've seen them around. If you look up in some polls, you should be able to identify those things. This is through three-phase power supply. So in this case, right now, these are electromechanical things. Actually, I think they're based on chemical too. They have oil inside. And what they're actually doing, if something happens in a part of the network, let's say a thunderstrike hit your wires, or a tree fell and created some kind of short circuiting among the different phases, this will create some kind of a problem like overcurrent, overvoltage. And when you expect 220 volts in your socket, you may have 1,000 or 2,000 volts arriving because of a fault. So what the devices are actually doing is they sense something wrong in the electricity. So if something is too much, there's too much power going through, then they automatically close. They actually open. They call it closure, but they actually open, isolating the fault, right? So the idea is that they continuously monitor electricity. If they find a spike, they sense the spike, and they stop the electricity from propagating any further. So the damage that has happened somewhere will not really reach your house now. It will stop at its source or wherever it started. And it will segregate the fault in a specific location. So this is important because, remember, electricity has a flow, right? It starts from the generation, goes to transmission, distribution, and reaches the customer. If something happens between generation and transmission, then everybody goes in a blackout, right? Because it's one way. It flows from the generation all the way to the customer. Because utilities know that, they kind of implement something smarter, which is connecting things in a loop. So instead of having just one station, one flow, they have two. One flow from here, one flow from here. So you have electricity being controlled at two spots, here and here. So if something goes wrong at this part, you have one wire going wrong somewhere in your city or in the rural areas, then you can have those reclosers. They can open here and here. So this will uniquely isolate the fault in only that location. So instead of having the whole city going down, you have one small neighborhood being affected because the fault has been isolated where it started from. In the past, the blackouts were just going everywhere. Now with this system, you're kind of putting things in a loop. So if you have some kind of an error somewhere, some fault appearing here, then those reclosers will isolate the error and make sure that the rest of the city, here and here, is not affected by this. Is there a question? So that's what the reclosers are trying to do. Until 10, 15 years ago, those reclosers were purely electromechanical. They had nothing smart about them. There was nothing you can do to remotely switch anything. So if you had those reclosers opening and creating the blackout, the isolation of the fault, in order to restore it, someone had to drive a car and go to the location, find the location where it is actually, because you don't know exactly where it is. You don't have transfer of data back to the control center. So you have to go around the city. Someone called you, and they say, we have a blackout there. So you kind of understand where the blackout might be and where it starts, because you have a map of where your substations are. So after they call you, you say, maybe I need to go there. So you take your car, you drive, and you see that there's a problem in that recloser there. And then you flip the switch back on, and then power comes back. That was in the old time. And this is not sustainable, and this is not something that you'd like, because the blackouts are lasting as long as someone needs to actually go, do this, recover, and maybe there's something else that they don't know. To make things smarter, what we're doing lately, that's why we call it the smart grid, those sensors, those controllers, actually those relays, are being controlled by a smart device. It's by a device that can connect to the internet, that can send you information back to your control center, and they can also do some advanced algorithms on checking whether the error is something that will just go away or it has to be stopped there at the source, right? So nowadays, these devices are connected to a controller coming from General Electric, from SEL, from a vendor, that if you have the fault there, it will report it back to the control center. So you immediately know within a second that you have the fault there, and you know exactly what to do and what to recover from your control center. You don't have to drive anymore. You can do it from your own place, right? But it's not very clear where the cybersecurity problems start, because when you add those intelligence, those smart capabilities, those smart devices, you can control it remotely, but also the attackers can control it remotely too. If they manage to infiltrate to your network, then they can manage to take over the device, and they can switch off the network as they please. So again, there's always a trade-off between making something smarter. It comes at the cost that if you don't do a good job in securing it, then you may have a problem by others actually using your infrastructure for their own malicious purposes. So our project was targeting those reclosers. The controllers of the reclosers tried to understand how to attack and how to defend the attacks from malicious sources. So back to what the project was trying to do. Again, first step is to create an environment in the lab that resembles what the outside world looks like in terms of the power grid, and gives you an opportunity to accurately assess what you're actually trying to assess, which in our case is cybersecurity concerns. So to start with what we're discussing before, you had the recloser, and as we said, the recloser is sending some sensing status to the controller, right? So it says I have a fault or not, and this is being read by the controller, and the controller is smart enough to understand what's happening and will give a command back saying, okay, now you have to open. You have to stop the flow of electricity because something is going horribly wrong here. And then the control center can send a remote command to the controller through the network. It say, okay, the fault is clear. It's okay now, you can restore operation. So you don't have to drive anymore. You can do it remotely. You can send the command to this thingy here, and it will resume operation. So this is what we're trying to do, right? So what we need to do, first of all, is we cannot really go and connect to the actual power grid. First of all, it's very dangerous for the students to work with kilovolts. They might die because of this. A lot of electricity actually can kill you. And second, we don't really need to. We just want to understand whether you have a problem or not, right? And the problem, it doesn't have to be in the kilovolts range. We can supply normal 220 volts and then make it to 50 volts as an over voltage situation, right? You don't really need to go after the high voltages. Actually, the recloser itself, before it senses the voltage, it downscales the voltage first. And then it tries to sense whether you have some error or not. And as we said, this device communicates to the control center in some way. And we discussed yesterday ways to do it. I don't know if you remember any. How can you communicate 30 kilometers back? We discussed a few ideas. We said maybe you point an antenna 30 kilometers. Maybe you have a wire, an optic fiber or a copper, but it's too long and you need to maintain it. You can do it through the internet. It can be a horrible idea if you don't do a good job in securing it from attackers. You can lease your own intranet by a company, and you do that. There are many solutions, and whatever fits your pocket, your risk analysis, and whatever your threats you think actually are. But in our case, we're discussing a setup where you have a point-to-point communication through GSM. So the network that exists everywhere has proper bandwidth, and you can actually lease lines from is what the mobile providers are doing. Wind, Vodafone, Cosmote, Greece, they have radio antennas almost everywhere around Greece. So you can piggyback on this network, use it for your own purposes to be able to communicate back to the network. And then you do that. If you have surrounding reclosures, you can collect the data in one concentrator and then communicate only through that. But that's a setup up to the utility. The way they communicate back is unique to its utility. But what we're trying to do in the lab, we're not concerned much about the network part. We're concerned about this. So this we don't touch. We just connect directly to a computer here. And then we have this setup. We don't really have to properly get a three-phase from the actual grid. We have our own current generation that you saw in the picture before. It supplies voltage to the device, and then we can we can turn on the voltage, and it will create some kind of a spike that will be detected, and the controller will say, okay, now you have to open. So this is our lab setup. This is the picture you saw before. It kind of resembles that. So you see some parts here. This is the device we've been examining. This is the data acquisition part, the laptop, and then these are the way we generate voltage and current. So now we have the setup. And since we're trying to detect attacks, we first have to implement attacks, right? How can you detect something that doesn't exist? So we have to come up with a way that something that shows some malicious behavior in order to be able to detect. And it's been a big problem because there are no benchmarks out there that you can easily take and port and say, okay, these are sample attacks. Malware, you can find malware everywhere, right? If you run malware databases, there are like thousands on the internet you can find. But some attacks for the power grid, because it's a very unique landscape, we don't know much about it, and we don't have many attacks about it. So we have to generate our own attacks. So that was the second part of the study. And in order to attack the grid, you have to understand exactly how the grid looks like. Because before security was even a concern, there was a bigger concern about the grid, which was its fault tolerance. Because you had, yes, a question. Oh, okay. Because there's, you also have natural things happening, right? There were disasters happening, or you have, as I said in the first lecture, you have animals eating the cables or falling into the transformers that can create some kind of a damage that will eventually create a cascading effect and potentially blackout. So power grid was designed to be robust against natural faults. So in order to attack, there's already some inherent robustness in the network. You have to understand what the network looks like, how it has been designed, and what are the critical nodes and where they are to be able to go and hit directly at the points you have to hit. So in order to do that, you have to understand the unique topological and the electrical characteristics of the grid. You have to know where they are, how long are the lines connecting them, what is the voltage that the lines carry. So you know that if you hit a specific node, the nodes around that won't be able to sustain the damage, because typically power is rerouted around. But if you cannot afford the load, the extra load you have, then you have to also start closing more and more things. You end up having a huge blackout in the city. And it has happened not by cyber attack, but it has happened in the Northeast by a cascading effect starting from Canada. It has happened in India in 2012. Millions of people were affected by a blackout that started by, I think it was a politician that gave free power to the northern region, and then everybody started using their appliances, and that created an overload situation. It brought down the network there and cascaded throughout India. So that was a huge blackout. So you have to understand the topological and, yes?
What about the Ukraine?
So the Ukrainian attack, we discussed it in the first lecture. So that was a cyber attack. That was an attack that it went through, so it was a multi-stage attack. First, they found the VPN credentials of the engineers. We discussed, remember how easy it is to get passwords from people, right? First of all, you can just ask them. Most of the time, they will just give you the password. And if they don't ask, you can find it through other ways. Password reshare, you can enter their computer, their laptop, you may find stored passwords there. That way you can get the passwords of the engineers. So they got the VPN credentials for the engineers, and then they use that to connect, and then they change the firmware of the modems. If you go back to this thing, this concentrator has to communicate with a control center, right? Actually, let me go to the real thing. This happens through a modem. There's a modem that converts serial to GSM, and this modem, the saying Russian attackers, we don't have this confirmed, but what the attackers did is they changed the firmware so you won't be able to access the devices. So at the control center, from the Ukrainian control center, the engineers there could not access the remote substations. So that had the effect that the attack was prolonged. You could not just flip it on. You had to drive like the old times. They had to drive and do it manually. So they overrode the firmware too. They found the credentials, and then they locked the operator's hours. They did other interesting things. They called. They had automated. They had machines calling on the phone, so nobody could report the outage. So they had people, not people, there was bots calling. So the telephone center was overflooded by malicious calls. Nobody could actually call and report, I have an outage in the area. If you don't report the outage, they don't know what the outage is. So it was a couple of days that they had no idea what was happening exactly, and they had to go around and investigate in person about the attack. And the attack was very carefully timed. It started December 23rd, after 5 p.m., so that's after you leave work to go home for Christmas. So everybody was going home, they had Christmas vacation planned, and then they started the attack right after every engineer left. Very, very well crafted, very, very well done, but it still didn't keep power down for more than a few hours, right? So that says a lot about the power grid, how resilient it actually is. We're testing it today, but it's more resilient than what journalists are trying to say that it's going to be a big problem, it's going to be bad. It's more resilient than what we think. So in your study, I stopped saying you have to identify the unique parts. You have to go and attack. So those unique parts, you can model them in a simulator. If you know where your substations, your generations, your circuit breakers are, you can put it in a model. Like this is, I think this is PowerWorld. PowerWorld, yes. We're using Math Power too, but this is PowerWorld. This is an open source simulator. It's not open source, but it's free for non-commercial use. You can model part of your network, and then you can go and flip things. So you can click here and say, okay, if that closes and that closes, what's happened, right? And you can't see the numbers. I cannot see it myself either. That this overloads. It carries more than it should. So if it keeps doing that, it will cause some kind of an actual physical damage. So the natural response to that is to just shut down. So once you have a lot of overloads around, things start to shut down automatically, creating a cascading effect that spreads the blackout throughout the city. So but you have to know exactly where to go and hit, which nodes to hit. And you have to know how many failures, how many problematic nodes your power grid can sustain. And that's called contingency. So in the power world, there's a lot of research on what is called contingency analysis. And that is to identify what are the unique spots you have to protect, and then add extra nodes to be able to understand, to at least contain one failure. So if one failure happens in any substation I have, my network will still work properly. That's called N-1 contingency. I can afford up to one problem. If I have N-P, then I can afford up to P. Critical parts, the big cities like New York, they have N-2, so they can afford up to 2. Typically, we see N-1. Depends on the criticality of your services offered in that part of the city. So the attacker has to find the number of failures needed to be able to cause the blackout, right? So first, the number, 1, 2, or 3. 3 is too much probably, and the actual location of the nodes. So this information, believe it or not, there's a lot of it publicly available for many reasons, right? It's not a necessary evil, but you can find information, open source information about, this is here the Emirates, Abu Dhabi and the Emirates, Cyprus. We have information about the US. There's a grid about Poland. There's a model about Poland out there. You can find this information online, and you can use it to model your own network. Why is it available? Well, for transparency reasons, for regulation reasons, for pricing reasons. When you sell electricity, you have to really tell the buyer what you're actually selling, right? What is your load? How much are you actually spending? So for all these reasons, you have to really output everything out there for everybody to see. This is not something bad, right? I'm not saying that you should not be publishing this, but you can do it in a way that preserves the information you like to give out, which is aggregation of how many lines you have, right? If you encrypt the data with homomorphic encryption, you can still add things together and have meaningful results without revealing the actual number itself. So what I'm advocating here is that public information is not bad, but it has to be carefully vetted before you publish it. And we have a paper we're writing now that was going to be published. We're going to submit it to CCS, and where we model a city. I won't disclose the name yet because it's sensitive information, but we found exactly all the buses that run through, the branches that the buses have, generation stations, the maximum load forecast, and the capacity of the generation. And then we mapped the actual topological. This is not a real geographical, but it does show the nodes, how they connect. And we identified the two parts that you have to hit in order to be able, because it's designed with n-2, you have to go to these two locations and have an attack there to be able to bring down this whole city. And everything we did here, we found it online, right? There's a lot of information you can find online on many, many fronts. So that was the first part, right? To attack, you need to understand how the network looks like. The second thing you need to know is what devices are there, because you essentially have to go and attack the device. To do that, there's also a wealth of public information you can find from success stories from the vendors. We're discussing the first module, that it says, okay, this substation has this Schlumberger meter, this is a multi-link processor, and this is Clinton Utilities Board. It's an electricity provider in Tennessee or Kentucky, I'm not sure. But they also, they record and they publish the committee meetings. So you can go and see what they're actually discussing in the meetings. Again, it may sound like a bad idea, but it's not. It's needed for the stakeholders, for transparency. There are many reasons why this is out there. But it can be used by attackers to extract information and be able to understand what the network looks like. So once you know what the devices look like, then you can find their firmware, because essentially you have to see what the firmware looks like, find vulnerabilities, and use them to exploit parts of the network. Yes?
When you said n-2 before, do you mean some two specific nodes or two random ones? Because in the diagram it shows two specific, I guess.
So when you design something for n-2, it means that the maximum number of failures you can tolerate is up to 2. That's any node in the network. So you may have a mix of n-1 and -2, but that's called an n-1. You take the least one, and you characterize the whole grid. So the firmware, you can find it online. Sometimes you don't need to authenticate. You can just say, can you give me the firmware? Then they just send you the firmware. Or you can just download it, or it's part of the software that controls the device. Or you can go to eBay, buy the device. You'll be surprised about how many devices are out there that people are selling for some reason. And we bought a few from eBay, and I always ask them, like, why do you have the device, right? Because you don't typically buy these devices and sell them. And we always hear stories such as, there was a project that got canceled, their decommissioned device we didn't need, things like that, but there's always the suspicion that they were stolen, or you had an oversupply and you just took it, fell off a truck situation, that you take it out and you sell it yourself, right? We bought a lot of devices on eBay, and much, much cheaper than what they're actually being sold by the vendors. And then we reverse engineer the firmware. That's a very tedious process, but through that we have found a lot of interesting things, such as default credentials, who has been the major problem, that everybody's using the same password, the same default password, and they never change it. We found vulnerabilities, such as the one we're going to report in Black Hat. So by looking at the firmware, you can understand what the device does, and you can use that to actually attack the device. So that's a lot of IDA Pro work. I don't know if you have used IDA. IDA Pro is a reverse engineering tool that you can open a binary and you can inspect its contents. Because a binary is a collection of zeros and ones, you don't know exactly if that's an instruction, if that's data. If you've taken computer architecture yet or computer programming, you would know that The machine code is hard to read. Then you have to make it assembly, but to make it assembly, especially with x86, is mostly not aligned. So you don't know where instructions start and end and where you have data. So IDA Pro is smart enough to give you, to understand where instructions are and to give you back an idea of how the assembly looks like. So it's a very powerful, and I encourage you to go and test it. There's a free version, a non-commercial version you can test. So sometimes the firmware we have is encrypted, which is good. It's a good sign that the vendors are doing a good job towards actually trying to have a proper secure mechanism. But you can still reverse. You can read my students. Harris, my second PhD student, he's been hacking devices. So you can find a blog he has, and he shows how you can actually go directly to the PCB, take the memory out, and then read directly from the memory. Because it may be encrypted when you send it from the software, but when it goes and gets executed in the device, it has to be decrypted. So it's decrypted and stored in the flash memory here. So we take it out of the PCB, we put it in our own adapter, our TSOF adapter, and then we start reading the memory contents directly from the flash memory. Second is to use JTAG. JTAG has been used for jailbreaking. A lot of hacks in devices like Xbox happen through JTAG. So we've been using JTAG a lot to get debugging information out, and you get a lot of information that's enough to be able to recover the whole firmware through JTAG. And the last thing you can do is just cryptanalyze, right? If it's encrypted, it could be a very poorly implemented encryption mechanism. What Microsoft had done 2000, I don't remember. I shouldn't say because the camera is recording. So a few years ago, the IntelliMouse firmware was encrypted, and the encryption was just XORing with FF. That's it, right? So if you XOR with FF back, you get the actual firmware. So encryption is one thing, but doing proper encryption is a very separate thing. And again, the Black Hat discussion is about a very poorly implemented encryption protocol that is, I don't know if you have done cryptography, I encourage you to go. Is cryptography offered in the university at any elective course? It's a very interesting topic, right? And the main I encourage you to take a look, because most of our problems today is typically poor implementation of cryptographic primitives. And there's a textbook, a list of things not to do. People are going and doing exactly that, right? Do not use your homebrew encryption. Always initialize your vector when you have a symmetric block cipher. Do not have linear transformations. Everything that we see that do not do, people just go and do, because that's the first thing that comes to your mind when you come up with your own encryption mechanism. So it's easy to go directly, easy. It should not be, but nowadays it's still easy to directly cryptanalyze because people are very, very poorly implementing security mechanisms. So the last part is now, first of all, we know the grid. Repeating, we know the grid, we know the devices. Now we have to find the devices and then attack them, right? In order to find the devices, you can either walk to the substation, if you can, break in the door, because they're typically unmanned. They may be fenced and may be locked, but there's nobody there. So if there are no cameras, you can just walk in if you want to. Or you can find things through the internet. As we said in the first module, many of these devices are connected to the internet for cost-saving purposes. So when they're connected to the internet, there's this search engine called Trojan, and I have it as part of the assignment too, but I'd like to go through a small demo of Trojan. Oops, didn't get the screen. Okay. So Trojan, again, is an engine like Google. It indexes IPs, but indexes devices, not computers. So anything indexed by Trojan is just a device. It could be your refrigerator, it could be your router, it could be a wind turbine controller. We find all sorts of things out there. So if we try to find a few things, explore. Now with the WannaCry thing, you can see the SMB and how bad the problem is, right? You look at these numbers here are staggering. These are thousands, hundreds of thousands of devices that are still out there. They have SMB that this WannaCry thing can go and actually do damage. It's phenomenal how bad the problem is. But this was not what I saw it in the morning. I was trying to do something else to show you other things. Most of the things we see on Trojan are webcams. You know, baby monitors. You have your, you want to check whether your baby is sleeping or something. These are not protected properly, and they have a lot of backdoors. So there are a lot of webcams you can find and see other babies. It's kind of creepy. But someone doesn't do a good job when they actually install the webcams, right? So you can see all over, you can find webcams, you can connect to them, and you can see a random baby if you want. Or you can go to industrial control systems, and you can start finding more information about devices that are exposed out there. I won't click, and I also encourage you not to be accessing those things, right? Just go there and understand the information, but do not access it. Because there's a difference between understanding the information and fixing it and actually going and doing something malicious, right? And again, we promote responsible disclosure. If you find a problem, you have to report it to the person so they can fix it. Do not try to exploit it. Do not try to access, because even accessing can create some kind of a problem to the device. So just observe, understand what's out there, and report it to the right authorities so they can fix it. That's called like white hat hacking, right? Be on the good side. Don't be on the bad side. We had discussions yesterday about whether you have to be, want to be malicious. There's no profit at the end of the line, right? Well, there could be money, but if that's all you're after, there are other ways you can make it, not through that. So it's important to understand what's out there, and I will encourage you to use Trojan as part of your assignment to find out devices that could be exploited by you if you wanted to, but I repeat, you don't want to, and you shouldn't want to. So, and there's a lot of ethical discussion. Is Trojan the right thing to exist, right? Do you really have to expose to everyone all those things? Again, my answer is yes. Exposure helps. Exposure accelerates improvement. I'm totally against security by obscurity. Most industry is. They think just by hiding it's enough. Academics, well, I disagree, and I think most academics will agree with me, that through exposure you actually get things done. And to be honest with this black hat thing, I actually saw it myself. Since we published it, then they fixed it formally, right? We had fixed it, but there was no advisory out. They were taking their time, things were going slowly, and when the abstract came out, then within a day, all the advisory was out. ICSR was notified, so everything was fixed on time. So back to the presentation. I won't keep you long, so Ramesh can also take over. I'll say one more thing, that again, Trojan is a way to find devices and enter the network, and then, as we said in the first lecture, protocols for industrial systems are inherently vulnerable. They were never designed with security in mind. There's no way to have authentication. There's some integrity, but even integrity is problematic. You can spoof messages very easily. Integrity was made for natural faults, not malicious faults. And there are many, every time we see a lot of advisories coming out. And to also show our thing, and I'll finish there. So this is what we have, what NYU reported, and our names are somewhere there at the end. So me and my researchers, we identified this and we reported to G, and G reported to ICSR. That's Homeland Security in the US. They really control this information. And what we found out, this is today's update. G came back to me today and said actually way more devices affected by what you found. So they're fixing more and more devices as of today. But this is, again, this is possible disclosure. We found it, we reported to G, they fixed it, the advisory is out, and then we present. And even during the presentation, we won't really publish the algorithm. We won't help the attackers do damage, right? The only thing we'll do is to pinpoint the weaknesses, say, do not do that, and do not do the other thing, to make sure that other vendors hear that, to make sure that the young researchers, right? One day, some of you could be the ones developing those protocols, developing those mechanisms, right? To have in mind that, you know, someone have found problems in the past, let me learn from those mistakes and not repeat the same mistakes again. So that's the point of exposing this. That's the point of responsible disclosure. So back to the talk, finish the attack. So you can model something together. You can find the units from the network. and then you can find the access path. And I'll stop here. I may stop with a video from the Aurora attack that we have. There was an example. It wasn't a real cyber attack. It was a staged cyber attack. It happened in controlled environment, but it shows that through the internet, you can actually destroy a generator. So this is what they do here. So I think I have sound here. This is all through the internet. They're sending commands to the device. So the Aurora, this is called the Aurora vulnerability or demo or attack or something. That was within a control environment, and they use it as an example to say, look, if you don't properly secure your infrastructure, someone can easily, from the internet, destroy it. And Stuxnet was an example that we saw on Wednesday. It destroyed centrifuges. It physically destroyed stuff. You can also physically destroy stuff here too. So with that, I'll open it up to a few questions if you have any questions and comments on this, or any observations. I don't like this room because I cannot talk to people. Right? Everybody's just sitting back. Yes?
From what you presented, there is quite a lot of information that is needed in order an attack to be performed. Are most, based on your experience, are most attackers insiders, bad employees,
That's a very good question, right? And this is why you have to very concisely define your threat model. What are you trying to protect against? Typically, the Ukrainian attack was definitely a nation state. Stuxnet was nation state. We believe that most of these attacks are nation state attacks. You have countries fighting, not groups. I think groups, hacktivists like Anonymous, have the know-how to do that, but they may be missing the budget to do that. They can find it through, well, this ransomware, probably someone has a lot of money today, right, because of that. But today, we still consider those threats mostly open to nation states, not script kiddies or hacktivists. But that should be part of your threat model. Oh, sorry, yeah, the insider part. So the insider part is the last thing of the chain, right? Because most insiders, they don't really know security. They can be a source of information. They can give you the password, but someone else has to use the information, right? I doubt someone in a company that has access to the control room understands security. So there's, because I've been talking to many companies on this, right? There's a segregation between people who work in the control environment and the security team that sits in their office back, the geeky guys with the glasses, and they haven't touched the device ever. But they know security, so they try to implement security mechanisms. So the insider could be the first step towards a nation-state attack. By either blackmailing someone, paying someone, threatening someone, you find a way. There was another question.
Regarding scanning for devices using Trojan, what's your opinion on scanning a local net for open ports? And what is your opinion on if it's ethically and legally okay to do it? Because there's a wide argument of it since forever.
There are two ways to scan, right? One is active, one is passive.
I'm talking about active scanning.
Active scanning has its own ethical issues. Even though we do it, I'm not advocating for it. Active scanning can create issues, and it has to be done only in a controlled environment. Nmap, to me, it's a dangerous tool, but again, I said in the coffee yesterday, knives are there, you can kill someone or you can cook. So you have to know the tools and use it properly. Same with Nmap, same with Zmap, which scans the internet, right? That's even more powerful now, that you can easily find this SMB thing is big. So maybe we can have a long discussion on the last lecture about the ethical part of hacking, right? Because essentially what I want you to get out of those discussions is that we don't do hacking for profit. We do hacking to improve and fix things, to make society better. So don't use it for personal profit or personal pleasure or to take revenge on your girlfriend who cheated on you or something, I don't know. People, there's a lot of part of blackmailing is through like old pictures of people, right? There's a lot of problems now. You have your pictures from your exes, and you blackmail them. I'm gonna put them on the internet. There's a lot of work trying to prevent that. So yeah, ethics, we'll discuss it separately. So let me stop here, since our esteemed colleague has to leave earlier, like 3:45 or something, so you can. So Ramesh will continue with a talk on hardware security, more generic stuff, because you got interested. Should we do a break, 5-minute break or something?
If he's in a hurry, then perhaps we can, without a break, we can go.
Will you survive?
We can take a break.
Okay, no,
Let's
yeah,
take a 5-minute break.
they look awake. Okay, they're fine.
Fine?
Yeah, yeah.
Yeah. That's what I need. No signal. That's good. Yeah. Okay. So, thank you for hosting me on such a short notice. Thanks, Mihalis, for giving up half an hour, 45 minutes of your presentation. I know it'll cut down on your, or you might have to extend your presentation some other time. Again, my presentation title, if you noticed, was on biochip security at some point, but then I said, after talking to you last night, give a little bit of overview of hardware security or hardware cybersecurity. And if time permits, I'll show a few slides on biochip security. This is probably a 30-minute talk. The other one is a 45-minute talk. And I have a bunch of those talks, but let's keep it simple and let's go with hardware cybersecurity. How much of you have a background in digital logic design, Boolean algebra? It's okay to shake it. This is one way of stretching your hands, right? Exercise. Yeah. Okay. So I think I'll focus. This is a different way of looking at digital logic design. It's interesting puzzles and interesting games is what I think it's about. So anyway, good afternoon, I guess. Good morning somewhere in New York. I have a meeting at 9 in the morning. But thanks for inviting me. Let me get my presentation straight. So over the years, electronic hardware has become the core root of trust for most systems, right? From buildings to your pets and everything in between, Fitbits and so on and so forth. That's one benefit, but on a different note, globalization of the integrated circuit and semiconductor supply chain in the last 2 decades has introduced numerous security issues. How many of you have taken a VLSI design class, or I heard Professor Hadzipoulos talking about cadence and so on, so some of that might make sense here. So I see one hand up. So we'll talk about the supply chain. So I won't assume any background. So I'll give you a little overview of everything. Yeah. And because of this, the electronic hardware root of trust is no longer trustworthy. So you can't assume that it's a good chip anymore. The systems that use them are no longer trustworthy henceforth. So what I'll do in this presentation, and you can stop me wherever you want. I have a bunch of slides. I don't have to go through any of these slides. I'll paint my vision of the emerging era of computer engineering, or as I call it, secure computer engineering, or trustworthy hardware, or hardware cybersecurity, whatever you call, and the implications of how integrated circuits and systems will be and should be designed. Okay? So what I'll do is I'll motivate hardware cybersecurity by presenting 2 attacks. There are many of them, but I'll present 2 and their impacts. And time permitting, I'll talk about 2 defenses, again using digital logic design as a background. So before I present the attacks, to understand the security problems in hardware, when I say hardware, I mean chips. Okay, let us look into a typical integrated circuit design and flow. Okay, so an IC design company typically has an in-house design team on the right-hand side. So they design some of the components. However, this design team cannot and does not design all of the components that go into an IC. As you will probably, if you have gone through the VLSI class or other things, you will notice that. So what they do is they buy some components from other companies. These components are typically called intellectual property cores or IP cores. And companies that sell IP cores are, you call them whatever name, I call them IP vendors. Okay? The design company also has an integration team. It may not be as distinct as the design team, but essentially they also have an integration team that puts together all the components together, all the IP together. And the design is synthesized into a register transfer level netlist, which is essentially a collection of components and their interconnections. Components at the highest level like adders, multipliers, and so on, and memory, and so on. So once you do that, this is then followed by logic synthesis, which results in a gate level netlist. So now they combine all of this and they synthesize it through some cadence tools. Then you see them as a collection of gates, Boolean gates like AND, NAND, NOR, and so on and so forth. Then it's followed by physical synthesis, which results in a layout. This is a collection of masks used to guide the fabrication steps in the semiconductor foundry. Then you get a layout mask deck, which is then sent to the foundry or the fabrication unit, where ICs are printed on semiconductor wafers, multiple layers, and so at the end you get a chip. And you get them as wafers. Each wafer has multiple chips. This manufacturing process is not perfect. In fact, it is imperfect. Hence, the wafers are tested for manufacture time defects. When you're manufacturing, there might be some defects. So fault-free chips are cut out of the wafers and packaged as ICs. The rest are thrown away. Then ICs are assembled into a printed circuit board, yielding a system. Suppose if you open your laptop, you see a motherboard which has multiple chips, right? So that's the high-level view of the design flow. Now let's look at what's happening. For a long time, before you were born, as in early 90s, I'm sure. So, system design process was vertically integrated. What does it mean? It meant that the design, the manufacture, the testing, and the packaging into chips, and assembling of the ICs into a PCB were all done in-house by a single company under a single roof. So they were all done by one company. IBM used to be one, Fairchild used to be the other, and so on. And then the products were sold worldwide. The IC technology at that point in time, compared to what we have now, was relatively simple. The feature sizes were about 10 to hundreds of microns. I don't know if you can imagine that. So that's relatively simple. Even micron is much smaller than what you can imagine. Okay? So now let's see what's happening today. Let's take Apple as an example. So if you can see on the top left, you see. Apple has design houses in Europe, China, and India. Apple manufactures its chips in a foundry in South Korea. Testing and packaging are done in Taiwan. Finally, the system is assembled in Silicon Valley. Apple products are, of course, sold worldwide. So all the IC and system design steps, as you noticed, are geographically distributed, unlike before 90s, where everything was done by a single company in a single roof in one location. And almost all the IC and system design steps are performed offshore. Compared, when you think of Apple, it's US based, so everything that I talked about, China, India, Europe, was offshore, right? Several reasons for several drivers, 3 key drivers. One, printing high-end semiconductor technology. When I mean high-end, right now it's about tens of nanometers, not hundreds of microns, in device dimensions, is resulting in high cost of ownership of foundries. For example, if you want to build a new foundry from scratch, it costs you about $5 billion today. And it gets obsolete about a year and a half-ish. So there's a problem there. The second driver, low cost of technically skilled labor in Asia. You can't compete, right? Some designer in US versus a designer in Asia. Third, and this is the most important thing, government subsidies in Asia, that you cannot compete. So if you need $5 billion to build a foundry in the US, you need to raise it by yourself. It's a private enterprise. But in the East Asian countries, the government subsidizes a lot of these costs. So there is suddenly there is an asymmetry in competition there. So this globalization of the IC design and supply chain has introduced several security vulnerabilities. Let me describe them, two of them now, okay? The first one is hardware Trojan. Here, an attacker can make malicious modifications to the design, and the objective here for the attacker is to insert a hardware Trojan is to control or modify or disable the system or leak sensitive information from the system. I'll give you a couple of examples. There are at least 2 scenarios where an attacker can insert a Trojan. Okay, so in the first scenario, imagine there is a bad apple or a rogue in an IP vendor. They can insert a Trojan. When you're doing a Verilog model or a VHDL model, you can add additional functionality besides the expected functionality. In the second scenario, the foundry can insert a Trojan. Again, it's not the foundry, but it could be a rogue in the foundry. And if you think about it, adding malware into a code is that much easier than adding making malicious modifications in the foundry. So I like the first malicious rogue in the IP vendor being a more plausible scenario. So the next question is, are hardware Trojans real? Right? For example, in 2008, Syrian radars were maliciously turned off when Israeli jets flew in the airspace. A hardware Trojan essentially disabled the radar so that the aircraft could go undetected. So this is a nation state. So now you can see if you buy stuff from somebody else, you could have backdoors and the ramifications of such backdoors. So that's one kind of attack. And as a digital logic designer, if you remember, there are lots of don't cares in your logic, and those could be used to bring in or build in additional capabilities, good capabilities, bad capabilities, malicious capabilities, or just plain bugs, unintentional. So let's look at the second attack. Reverse engineering is the next attack. Here, an attacker tries to identify the device technology used in an IC, or its functionality, or the design. Reverse engineering facilitates Trojan insertion. Once you reverse engineer, you know places where you can add additional circuitry. It can also enable piracy. You can take the design and then you can rebuild your own design and so on. Anyone in the downstream of the IC design flow can do reverse engineering. For example, the SoC integration house, when they get multiple IPs from different IP vendors, they can potentially reuse some of the IP that they bought. Or the foundry, because when you you fabricate chips, you actually give them the entire layout deck so they can make any modifications, they can insert Trojans and so on. Or the end user. So what does reverse engineering mean? typically, the reverse engineer takes an IC, depackages it, delayers it, images those individual layers, annotates them, and analyze the images and extracts the design. So that's the process. And it's not that difficult. Even at 10 nanometers, they can reverse engineer a large Intel chip, 22 nanometers. Every time there is a technology, there are tools to reverse engineer at that level of complexity as well. So there is a company, in fact, called ChipWorks that performs reverse engineering, but they do it to detect piracy. So if you suspect that some company stole your IP, what you do is you take their chip and give it to ChipWorks, and they reverse engineer it and present it in court and help you win or win some damages, right? So the impacts of reverse engineering, so this is for the good guys. So it's legal, by the way. And of course, once you have these capabilities, somebody else can use it for illegal purposes as well. So now let's look at the impact of these attacks. To understand the impact of these hardware-based attacks, consider these various layers in any modern information processing system. Until now, attacks have been common at the user, application, operating system, and hardware level. At the user level, social engineering attacks, right? So they send you an email, phishing emails, and so on. At the application level, it's the malware. At the operating systems, it's the rootkits that get into your operating system. Hardware level attacks are beginning to happen. I have given you a couple of examples: backdoors, reverse engineering, Trojans, and so on. Now let us look at their relative impacts. What do you think is going to have the most impact?
Hardware attack, because we can destroy hardware, we can create some physical damage, and because I believe can capture every information that goes either in the operating system or the application.
Okay, that's good. Anybody else?
Isn't every state as important?
Okay. Anybody else? No wrong answers, by the way. Yeah. Yes.
I would say hardware too.
Hardware too, because see, the best guess for these answers is, since I'm presenting something on hardware security, it has to be hardware, right? Having said that, all of those are equally important, right? So let me make a simple case. How many of you click into a phishing email? All of you, well, you can raise hands. I've clicked multiple times. Okay, thanks for volunteering. Yeah. So if you look at it, 1 out of 10, right? So imagine the impact on a scale is 1 to 100. So not everybody has raised their hand, right? Application level, how many of you think got infected? Every time I see 2 more hands, but if we are true to ourselves, there are a lot more applications that are running that you don't know on your laptop, because you download something else comes in. And so that happens. Operating system level. Rootkits, once you install a malicious operating system, it spreads all through, so maybe much more impact. My argument is that hardware has an equal impact because of the reasons that you outlined. Once you bake something in a chip, unless you take it out, it doesn't. It's sitting in there. And again, yeah, probably none of you were born when there was the Intel bug. There was a bug in the Intel Pentium in the floating point at some point in time. Initially, they said it's going to be rare and so on, but the impact at that point was significant. They had to bring back all the chips and so on. And the other thing that happens between hardware and software is, anytime you have a bug in software, do you get any money back or anything from Microsoft? No. But anytime there's a bug in a chip or a system, you can send it back. So somehow they had that deal. So in that sense, hardware impact is that much more, or at least the same order of magnitude as OS level, and so on. And we can debate, and I don't disagree with those who think it's about the same level. But so these are the kinds of things. The argument is, at least it's quite important, even hardware level vulnerabilities. That's the point here. Okay? Good. So hardware cybersecurity, or secure computer engineering, as I call it, is the emerging discipline that is forming around the efforts to make electronic hardware trustworthy. So what I'll do here is talk about two defenses that we are developing. There are many more we have developed, but they're broadly called design for trust. Okay? For those of you who have done VLSI testing, there is a theme called design for test, and this is design for trust. To guide through these defenses and their applicability, consider this table. It's a very simple table. You have the foundry and the user. The foundry can be trusted or untrusted. The user can be trusted or untrusted. And I'll use this table to situate the two design for trust techniques. In fact, you can use this table to situate any design for trust technique, and you can also make it a little more complicated by having additional dimensions. Designers, for example, are not part of this thing, so designers could be trusted or untrusted, but let's keep it simple. So I'll talk about two techniques. I only talked about two attacks, right? Trojans and reverse engineering. Right here, there are 4 defenses. Counterfeits, it's an interesting counterfeit ICs. Yes, go ahead.
Sorry, I don't get the idea of untrusted user. If there is a hardware Trojan, it's the user that has a problem. So what's the meaning of untrusted user?
Good point. So hardware Trojans is potentially an untrusted foundry, right? So essentially you have to assume something about, so you won't have you may also have an untrusted user and an untrusted foundry. What are the attacks going to be if you look at that, and how can you defend against somebody who is an untrusted user and an untrusted foundry? And this is of concern to designers, right? The designers are designing some IP, and when they fabricate it, the foundry could insert Trojans, and when it gets sold, somebody could reverse engineer it. So that is where this thing falls, right? And if you have just hardware Trojans, you can assume that the foundry is untrusted. That's where the Trojan is inserted. And you assume that the user is trustworthy. So these are the various ways you can classify the threats and classify the defenses, right? Okay. So I talked about 2 threats. Piracy and outbuilding, I vaguely alluded, but Trojans and reverse engineering. Counterfeits is a huge problem. I can go on and on counterfeits. Anyway, let me skip that. So I'll talk about 2 techniques, camouflaging and split manufacturing. So let's get to camouflaging. So every time you come up with a defense, you need to understand your threat model. Here we assume that the foundry is trusted, and the attacker is the user. You have an untrusted, so the attacker is the user. So I see camouflaging is a technique to defend against that class of threats. And I'll go ahead and explain this more. So how many of you have seen something like this? What do they stand for? Did anybody do layout and so on? Yeah. So those are standard cells, if you remember. These are the physical layouts of individual gates, and you replicate them to build a function. So I'll go back to the logic level so that you will see the relationship. Okay. So IC camouflaging is a layout level design for trust technique. It is used to thwart the reverse engineering attack. So the attacker is the user, he does reverse engineering, and we'll explain what that means. So ICs are typically designed using a library consisting of pre-designed standard cells. Examples include NAND, NOR, inverter, buffers, D flip-flops, T flip-flops, and so on, right? So these are, when you do digital logic design, they say optimize it using NAND gates, or implement a function using NOR gates, or buffers, and so on, D flip-flops, and so on. So because the functionality and the structure, so if you look at the structure, typically, carefully, The NAND has a different structure than the NOR. And if you use a lot of NAND gates, you can immediately identify, you look at the structure and say, oh, that's a NAND gate. So the functionality and the structure of the standard cells are highly correlated. That's a key observation. They are easy to, hence, reverse engineer. For example, if a reverse engineer encounters a structure like on the top left, anywhere in the layout, he can determine that it is a NAND gate, right? If he encounters something like the one on the right, he can determine that it is a NOR gate. And you can then figure out the circuit, and so on. So now look at, so what's the difference between the top, those two standards? Do you see any difference? This is only for those who are awake. No, right? Yeah, what?
I think there's an extra layer of metal or something.
No, just those two. Forget about this.
Those two.
Between those two.
Oh, I don't know.
Stare at it a little more. Just make a guess to make me happy. No?
Probably it's difficult to distinguish which one is that.
No, forget about just the pictures itself. Do you see any difference in the pictures? No difference. Good answer. There's no difference. Okay, so these are camouflage standard cells. They look alike, right? So there is no difference if you look at it. So you are the attacker. You're looking at those two gates. There is no difference. Yeah? But their functionality is different. For those of you who have done layout, this is a difficult thing, right? They look alike, but the functionality should be different. So if the functionality is different, but they look alike, it's hard to reverse engineer. Right here, you see this thing, and you say, oh, that's a NAND. Oh, that's a NOR, so I can figure out the gates. So here, the NAND and NOR cells are designed to look alike. They are carefully designed to look alike. So that's a good challenge for those who are doing layout, right? How to do that. Hence, when a reverse engineer sees the structure in the layout of he cannot say if it is an AND gate or an OR gate. However, the problem is, to design something like that, it takes larger area and so on. So we'll go and look into this a little more. So do you think we can design something that looks alike but functions differently?
Maybe with different materials.
What about if it's the same material? So with different material. Yeah?
So it has different connections, the bias.
Beautiful. So you saw my slide here. That's fantastic. See, that's that. So if you look at this, I call them the dummy contacts, right? So contacts go from the metal layer to the poly and so on. So one way to construct camouflage cells is to use dummy contacts. When you okay, this is the side view. When you cut, most of us know how to cut a cake, right? You cut it this way. So, so if you look at the left, you see that the contacts span all the way from M1, which is metal 1, to poly. So you have real contact connections through the vias, right? Now look at the right-hand side one. There is a gap in the middle, right here. You see that? So, but when you look at from the top, they look identical. Yeah? So reverse engineering, they essentially take top view and peel off the layers, layer of the layer, and take images and redo the stuff. So if you know your threat model, which is reverse engineering by taking images from the top, a few dummy contacts like that cannot be detected. Or they can be detected if you go all the way down there, right? You have to peel off layer by layer, and it takes you a lot of, and as you go peel off multiple layers, it becomes more and more noisy, the data that you get out of this, the images that you get out of that. So that's one key idea of camouflaging. So at the top layer, they all look alike. Maybe at the second layer, they look alike. But at some point, they have to look different to be implementing a different functionality. And that's why it's called camouflaging. Yeah? And to do that, it takes extra area because you have to initially put these dummy layers, rather the identical looking layers, but at the bottom, you still have to implement both functionalities. Yeah? Is this clear? So by the way, this is a proprietary technology of Cipher Media. They have about 40 patents. And now let's see how we can use camouflage cells during the design. Yes?
What about the cost of these extra materials?
We'll get there. So what do you think is going to be the cost? So I'll ask you the same question, right? What do you expect the cost to be? Did you say cost? Yeah. What do you expect it to be?
The camouflage, the ICs are going to be much more expensive.
Why? Because of more size, more area, and so on.
More metal,
More
yes.
metal, and they also might consume more power, bad stuff. We'll get there. So I'll give you the numbers. Yeah? So, but if there was no cost, ignoring the cost, what would we do? You remember we were at the gate level netlist at some point during the design flow? So then what you could do is you can either replace all the gates with camouflage cells or some of them with camouflage cells, a trade-off, right? Because assuming it's costly, you might want to pick some of them. So that's why you have standard cells and camouflage standard cells library, and you then pick something and insert them into the gates, or rather use some of those standard cells, and then you go through the gate level netlist, you manufacture them, you package them, you get your chip. Yeah? It's costly, expensive, all those things. So what does the deep design attacker do? That's what he does, right? The attacker depackages the IC, delayers it, images those individual layers, annotates them, and analyzes the images and extracts the design. However, he does not know what that question mark gate is because, right? It looks like an AND, it looks like an OR. He does not know, right? Even assume that he knows that it is a camouflage cell that implements two functions, NAND or NOR, right? So the reverse engineer is then forced to guess what that gate is. Yeah? Now you see yeah.
What if it just uses the gate with actual data and they figure out that it's a NOR and a NAND?
Beautiful. So that's the so how will he figure it? So I gave you a big chip where only 20 gates inside the chip are camouflaged. How will you figure it out? I have 1,000 gates. I only camouflaged, I only camouflaged 5. If I camouflage all 1,000, it's impossible for you to figure out, right? 1,000 inputs. Suppose there are 100 inputs to the chip. What would you do? You try all 100 combinations, 2 to the 100, right? Not 100, 2 to the...
Yes.
Yeah, so...
Step by step.
Step by step. So let's count how much time will it take for 2 to the 100. Let's do that. Each takes nanosecond. Let's make this, that's a good number, right? 100. Let's make it 128 or 100, 2 to the 100. Yeah, think about it. Let's stop there. That's a beautiful question. I think...
Some nanosecond times some nanoseconds.
Pick whatever number. Femtoseconds. It doesn't matter. That's the time it took for the universe.
Too much time.
Yeah, so you say step by step, let's take it. So you have to, it's the whole time that it took for the universe. Imagine you put 1,000 gates camouflaged out of a billion gates. 2 to the 1,000 is huge number to get the functionality. I think that's the point there, right? I gave you an example with 10 gates with one thing. It looks obvious, right? Because that's the best way to explain. Do you see the difficulty? Because you have to guess all the gates, their functionality. I even tell you that they implement only NAND or NOR. So 2 to the 1,000. Imagine if they can implement one of 3 functionality. 3 to the 1,000, NAND, NOR, and XOR. Or XOR, NOR, and something else. 3 to the 1,000. Suddenly, as an attacker, it becomes that much more difficult for you. Yeah? So this is digital logic design. So yeah. So where am I? Yeah. So you said brute force, it won't work. The next question is this practical? Is anybody using it? Is it something that we made up? The answer is it is practical. It is a technology developed by SMI over 140 million sometime back. camouflaged ICs are in products. TSMC, the chip foundry, does support camouflage standard cells, and so on and so. You use them in, typically you are used in chips and set-top boxes, by the way, because cable industry is one of the most aggressive industries in terms of protecting their IP, because none of us want to pay for cable, right? We all want free cable. No? I want free cable. And about 15 years ago, you used to go get it from your neighbor. Then they used to change the password, so then they gave you a smart card. So they were playing back and forth, and at some point they said, okay, let's do camouflaging so you can't get these IDs and so on. So set-top boxes are one place where camouflaging is used extensively, and of course you can assume that DoD, defense fund companies and so on. But somebody asked cost, right? So I'll get to the cost. So what do we do? So now I want to be with you and see how we can break it, right? So what we did was we developed a methodology to evaluate the security of camouflaged ICs. We first analyzed and modeled the capabilities of an attacker. We said, what would an attacker do? And then we developed metrics to quantify how the attacker would attack. And then we used this metric to engineer defenses, to carefully put these things at different places. Okay? So what are the capabilities of an attacker? So we give the best capabilities for the attacker. You don't assume that the attacker does. So one of the mistakes we make is, oh, I won't tell you what I do, so I'm okay. It's like the cat closing its eyes and drinking the milk and thinking nobody's watching it, right? So you got to make it public. So you assume that the the attacker has access to the camouflage netlist. He might have obtained it by reverse engineering the IC, for example. In this netlist, he knows the question mark gates, right? He was stuck at that point. He knows the netlist perfectly, got it. He wants to figure out what those question mark gates are. He does not know their functionality. He knows it's an AND or an OR, but he does not know which one it is. He has the library. He also knows that this library supports camouflage cells of two types, right? It can implement an AND or an OR, maybe some other library, 3 functions, and so on. And he has the IC that he got from the market. As you pointed out, apply inputs, observe outputs, and so on. So you have all these things. You have a functional IC. You have the netlist. You want to figure out the question mark gates. What? Yeah?
Then someone, the attacker, check for inputs and outputs and make out a hypothetical truth table and then like slowly like test different combinations, but like it's not like brute force because you develop some logic behind it while just crossing out some options.
How would you do that? I think that's about the idea. So you got to be careful, right?
Yes.
Yes.
It won't iterate like by going through, say, like it won't be like testing all the possible solutions, but we just cross out because some will overlap maybe, some won't matter because of the way the whole integrated circuit works. And as far as since you get the integrated circuit, you know from the library or from the documentation for what input you get what output.
Mm-hmm.
So I don't know, maybe this could work.
Maybe, right? So that's good. So now so you are thinking attacker. What would you do as a defender to protect against you? Right? You were just thinking like an attacker. What would you do to protect against what you just said?
Obscure more information.
No, that's always a bad idea. All of this information is there. What would you do, right? Hiding not talking to me is not an option. Because this is, as he showed, you can Google and get a lot of this information. You get your public, the data sheet, right? So what do you do? So
make it very complex, I guess.
no, this is the circuit. So what, right? I mean, so this is a good question, right? He immediately came up saying, we may not need to test everything. That was his short answer, right? What would others, if you were defenders, what would you make him do? camouflage all the gates. What would happen if you suppose, so that's expensive. If it's not expensive, you're stuck, right?
But if he has enough money to camouflage all the gates, maybe I'm an attacker with enough resources and enough time and enough money to brute force it.
Enough time is not there. There's not enough time there. We just talked about that time, right? It's not about money anymore. There is not enough time because the whole world is, it's since when the whatever the
Make parallels and maybe split the.
do that. So to take this number 2 to the 128, I'm just giving,
It won't work. I agree.
parallelize it, and every atom, so I'll give you, so take every molecule in the world, assume each of that molecule is your computer, right? That's the best parallel computer. All the molecules in the world, nothing is wasting or sitting idle. Then do parallel processing. That's reasonable, right? That's the best parallel processing. Every molecule, every atom works for you. Even then you cannot, 2 to the 128 is such a large number that even if you parallel process on those, even if each of them takes femtosecond, nanosecond. So you should play with this number 2 to the 100 or 2 to the 128, right? 128 is, that's AES crypto. So some of you who have done crypto, you will notice that, right? So, yes?
Do you use the same pattern for the same device like the gates that you hide, or you like do it randomly?
Yeah, same device. Yeah. So all devices, same pattern, same.
Yeah, but in that way, if by mistake I find the correct gate sequence,
You're
I
lucky.
can hack everything.
Beautiful. So that's good. So the chance that you'll be lucky if I insert 128 gates is 2 to the 128. 1 over 2 to the 128. It's better you go by lottery than winning. You'll buy lottery win lottery many more times than being lucky. Of course, if you're lucky on this, you better be lucky on. Yeah. 2 to the 120, 1 over 2 to the 128 is the chance that you'll be lucky.
Wouldn't getting to the source of the problem like the manufacturer talking it?
You're changing the threat model. We made, right? You can't change the, so that's why we upfront said, you are taking images. That's all you can. Of course, if you go and ask the original designer, what did you put? That's easier. What did I force you to do? I force you to do something else. Yes. This is, I think I'm done with my lecture, because these are the questions. I had one more defense, but I don't need to go through that. So, any other questions? So we'll go through just this defense, 5 more minutes, right? Yeah, so I have enough. So this is what I want to figure out, right? I have a camouflage netlist, I have the library, I have a functional chip. We all agree this is a reasonable assumption. You buy it off the chip, and I want to figure out the IP. Because once I get something like this, I can sell it, I can do my, make modifications, make it better, and sell it as my own. And what do we do? So, so this is basic logic. So now let's talk about the defense, some basics. Let me explain how the attack works, right? So I have a question mark gate, and it can implement either an AND or an OR. Assume that's what the function, that's what this does. Look at the truth table, something interesting comes out. If you have a 0, 1 or a 1, 0, right? Suddenly you can tell what gate it is. You see that? So if you apply, suppose you have a single camouflage gate, you can directly apply inputs. If I apply 1, 0 and I get a 1, I know it's a NAND gate. This is Boolean logic, right? And if I get a 0, I know it's a NOR. You had a question, no?
Yes, that's what I was talking about.
I know.
We don't know which are the camouflage gates, so we can't do that.
So I'm starting slowly, right? So if I have a chip that has one gate that's camouflaged, we broke it. And so these, I call them the differentiating pattern, right? So you can distinguish between these. And you can do the same thing. So those are the DPs or differential. And then you do something else, the common patterns, right? They provide the same output regardless of what gate it is. I don't care anymore. If I don't want to know what this gate is, I can apply a 0, 0, or a 1, 1, right? So I can bypass this gate in some sense. So these are the two things you'll notice, differentiating patterns and common patterns. What can I do as an attacker with that? So now let's look at this design. I have two gates. What would you do? Now that you know, how would you figure out the functionality? What inputs would you give to C1?
For example, 1 and 0.
What? Yes, one of the either 1 and 0 or 0, 1, right?
Yes.
Beautiful. So let's say the unknown value of C1 is X, unknown value of C2 is Y, output, right? X and Y. So I need to justify the inputs of C1. 1, 0. You said 1, 0, right? I'll give you 1, 0 there.
Keep all 4 of them.
No, no, no.
0, 1, 0, 0, 1, and 1, 1.
Yeah, I know. Let's do one at a time, right? So let's do 1, 0.
1, 0.
But you can't observe X, right? You only have access to the output. Your chip, you only see the.
I can't see the X. I can't take the output somehow.
How do you stake somehow? There is no way because you have a real chip. Or you have a gate level netlist. You see? So you cannot poke, so if you have billion transistors, you cannot, or gates, you cannot poke internal points. You only can apply inputs at the primary inputs and observe the primary outputs. Yeah? You see that. So you cannot directly observe X. Where can you observe X? At the output. So what do you need to do to observe X at the output? If you put a 1 there at the input of G5 somehow, again we don't know how to put that, right? Then you get X bar there. If you see X bar there, then you can figure out the functionality. And you can do the same thing for the C2. You put a 0, 1 here, right? Remember 1, 0 there, C1. So what happened? I can find Y bar. So what did I do? I needed to propagate the outputs to the primary output. So I set a 1 there so that the other the side inputs of the gate. Now I can use basic digital logic design, but for large things, you use an automatic test pattern generation tool. This is VLSI testing, but for this small design, you can figure out there are multiple choices you can do. So what you could do is something like that. You can fill up the other, you can pick other gates, other values too, right? So what happens if O1 is X? If O1 is 0, you see O1 as a 0. Then what can you say about C1? What gate is it? It's an AND gate.
So it only outputs 1 when the inputs are both 0.
So if that is a 0, then X is a 1, right? If X is a 1, and if the inputs are 1 and 0, it's an AND gate. And then if O1 is a 1 instead of a 0, then that's a NOR gate, right? So depending on what you see at the primary output and what you applied, you can figure out if it's a NAND gate or a NOR gate. Similarly, you can figure out for C2. Okay? Now let's look at this example. Very simple example. So what would you do for C2? So let's target C2. Take 1, 0, the differentiating pattern you want to figure out, right? What the function is. For C2, let's apply 1, 0 there, right? Then if it is a 1, you know it is a NAND. If it is a 0, you know it's a NOR, right? Using the table right there. If you see, I put 1, 0. If it's a 1, that's a NAND. If it is. So what happens? If you need a 1 there, what do you need at the input? So the input to G1 should be? Both inputs should be a 1. Yeah? Then what? Setting the inputs of C1 to, then you don't want to care about C1, right? Hide its functionality. How would you hide its functionality? Using the common patterns. You put either a 0, 1 or a 1, 0, right? Sorry, 0, 0 or a 1, 1. So because you're just focusing on, yeah? So let's try with this, 0, 0. Contradiction. You can't figure it out. Yeah? So what happened? Now you have to guess the other value. What did I force you to do? Brute force. Right? In the previous case, it was easy to figure out the functionality. Here, this gate is protecting that gate, and that gate is protecting this gate. So at the end, you have to try all combinations. If this is a small design, if you have a large design with gates that protect each other, and if you have 120 of them or 100 of them protecting each other, you can't do much as an attacker. You see that? And so essentially, this is a design. So the metric is, what is the size of the largest clique of gates? A clique is collection of gates, C1, C2, C3, that interfere or protect each other, right? So if C1 is protected by C2 and C3, that is to figure out the value of, to figure out the functionality of C1, you need to know the functionality of C2 and C3. To figure out the functionality of C2, you need the functionality of C1 and so on. So then you have to try all 8 combinations, right? 2 to the 3. Here, it's only 2 combinations. So suddenly, now imagine something like that, right? It's 2 to the 4. Now imagine you have 100 gates that interfere with each other, 2 to the 100, and suddenly we protect it from your attack. Yeah? Yes?
These gates that they influence each other are usually close to one another. What if the attacker wants to attack to another part of the chip?
So they don't have to be close to each.
Ignore the camouflage gates. What about that attack? What about that attack? If we ignore the camouflage gates because they're all together in one part of the chip and we attack with the other part of the chip?
They need not be on, I'm just showing you a small example. They could be all over the stuff, all over the gate, all over the regions, right? They don't have to be like next to each other. They could be far away too.
Far away, but they influence a specific input route. What do we if we choose another path without camouflage gates?
Yeah, you can choose another path for you might, so as a designer, what would you do? So I'm asking you the opposite questions, right? So how would you defend against what you just mentioned? You make sure that your camouflage gates are spread over the entire circuit in a careful fashion that you won't get most of the circuit functionality. Right? That's your challenge, as my challenge as a defender. Yeah? You don't want to keep them in one corner. You want to spread them in a reasonable way. And there are algorithms. So all of the randomly select a gate, add it to the list, repeat until enough gates are camouflaged. This is a simple heuristic, and you can come up with something much better, right? Yeah. So I'll skip this. So what we did is we did some random stuff, and we also did some smarter stuff. So we took a circuit, we said 128 gates camouflage. If you do random, the click size is only 28 out of 128. If you are careful, so where am I? So right there, that tells you the size of the largest click. So a better heuristic gives you a very strong camouflage thing. Out of lots of gates, I only camouflaged 128, right? So suddenly you have a click of size 128. So, and we did this for lots of examples. It looks good. So that's the message here. You know everything, but you still don't know how to figure it out. Yeah? Does that answer your question? And how do you do it? There are many algorithms. I'm not going to you can come up with a better one. The next question the final question, results, overhead, this is the question you have. We only camouflaged if you camouflage just 5% of the gates, the overhead is about 100%, 105%, too much. So you cannot camouflage every gate because of that. So there are several directions you can go. Come up with low-cost camouflaging, whatever it means, I don't know. Come up with better places of placing these camouflage gates, or come up with other ways of camouflaging and so on, right? So what we have done here typically is we took a processor and the controllers, there are lots of controllers in the processor. We just camouflage those rather than the data path. So the controllers are typically 1% of the processor, but they control the operation of the system. So they are the critical pieces, and we camouflage them. Controllers are tiny, camouflaging controllers, although they're power hungry, 5x power hungry. You see, the area of it is 105%, and the power is 5x. Lead to small overhead. So without controllers, the data path is rendered useless. So that's all I have for you. I have one more technique, but I won't even go into that. I think this is good. Yeah? So there are a bunch of other techniques. We can do split manufacturing. I'll skip this. I'll just, if people don't ask questions, I rush through the slides. I'm glad you stopped me at that. Otherwise, I could have talked about split manufacturing without you caring about it. So vision, so what do you need to do? When you're looking for security, you want to make sure you do design mindful of security constraints at every step, during standard cell design, during layout, during RTL, during gate level, during architecture level, of course, secure software. That's the message I have. Thank you. We talked about this yesterday, right? Embedded challenge. So I won't, I won't even go into biochips. This is good enough, right? Huh? I know, so. Yeah, so I'll leave it at that. So all of this stuff. So I have lots of these motivational slides there. Yes, it is important, believe in it. And all of you who do logic design at the front line of defense, and security in hardware is not difficult, as you saw. It was a simple problem, right? Once you frame it carefully, we started the numbers, we figured out that these numbers include you if you do the whole universe to help you out. Answer.
Ideas like the algorithm could help to prepare solutions for this kind. Where should the
We use some of those, and so the better algorithm. So there were two algorithms. One is randomly insert stuff. The other is use ATPG, the test pattern generation, to inform propagation, justification, all of VLSI testing algorithms. So we use ATPG tools to identify locations, and that's where we get the maximum stuff. Yeah. So that's where the linkage is to the VLSI testing. Okay.
Okay, let's thank the speaker again.
Thank you. Thank you for participating. I enjoyed it.
Let me finish 2 minutes with the assignment. So we go on. Gonna run now or wait?
Yeah, I'll send an email saying I'm running late.
Yeah, we'll leave it 5 minutes.
Yeah, okay.
Yeah. So, just to finish with what I'd like you to do for, again, whoever is registered for the school and will want to get a certification at the end. Let me bring up the slides. I think that was more fun, actually, than what I'm saying. So we should have started with this instead. Your talk. More interesting. All right. So, I don't know. No? Maybe it's where you were sitting before. Yeah. All right. So there are two assignments, as I will describe when the school announcement came out. One is a presentation, and the second one is a report following the presentation. So the first is an assignment you'll present the last lecture. It will be more of a discussion-based lecture where teams will present their own investigation into ICS security, and everybody else will learn from them too. So I'd like you to form 5 teams. I'm not sure what's the best way of forming. You can either have your own team already, or you come to me and say, just assign me in a team. And there are 4 issues I'd like us to investigate. One is manufacturing, second is medical devices, transportation, water treatment, and wastewater too, and then emergency services. So the presentations, you sent it to me by 29th. I'll give you some feedback in that lecture, and then you'll present on the 31st. The presentation itself should be around 30 minutes, tops. And you should definitely include defining the problem, right? What is critical infrastructure security? What are you actually going after? Has there been any history of events or incidents that we know already of known attacks in any of those critical domains we discussed? I'd like you to explore Trojan a bit, the search engine I showed you. Sign up. There's a free version. You sign up. You can have a few credits. You can do some searches for if you in critical manufacturing. Try to find the top vendors that sell to those companies. Yes?
Presentation should be done in the language.
It's up to you. I won't say Greek or English is fine, but the report has to be written in English. I think it's a good idea to write in English too, your presentation. It could be also, better for you to improve your English as well. Could be a good chance. Then some discussion about current trends and vulnerabilities. What's happening in that domain, like the critical infrastructure, in the water treatment. Are there current threats? Do we know existing vulnerabilities out there? Take a look, try to find problems. In some cases, you may not find anything, right? Don't be alarmed. Just report that. Say there's nothing we know, and just report on what you actually people are talking about. Defenses, also take a look whether people already have some defenses. There are already a lot of academic work on mitigating many of these attacks we discussed. So take a look what people are doing and what has been done already. And last but not least, future work, right? What needs to be done? I want you to come up with an action plan. If tomorrow you get assigned to be a security engineer in one of those critical infrastructures, what would your first steps be, right? What do you think the next steps should be towards actually doing this right? Towards fixing the problems, towards ensuring that the risk is minimized, towards ensuring that in the future you'll do anything required that no security concerns be there in the first place. So that's all I had. I don't know if there are questions about this. If not, I'll come down, you come to me, you tell me your name and whether you have a preference on the topics or not, or whether you're going to form teams. Alki?
You said 5 teams times 30 minutes means 2.5 hours.
No, 150. It's 2.5 hours, yes, exactly. So we'll do it less. Actually, I thought it was, yeah, you're right. No, we said 2 hours, it should be 2 hours.
Just to arrange for the...
No, let's do 20, 25 minutes.
We can leave it 30, I will arrange for 2.5 hours.
No, I think it's, since we said 2 hours, we don't need to take our promise back. 20 minutes presentations. I'll write in my email too.
Would you like each person of the team to speak, or would it be one central presenter, or is it after?
It would be nice if everybody speaks. I don't know how many presentations you've done in your academic life yet. One complaint I had for my undergrad studies, I never presented anything anywhere. And once I started my PhD, I was just standing like, just didn't know what to say. Like, what do I say now? So it's good to get some practice in presentation. You had to see me when I was presenting my thesis. It was ridiculous. So yeah, everybody should say a few words. All right. So for the teams, again, take a look. I'll come down there. You come to me whether you have a preference or not. Or how many people are here? I mean, I think originally 22 signed up, and then 4 added, but some people left. So it should be around 4 people per team. That's what I can see.
Will you do the final team assignment? Because,
If it's not working out, yes, I'll do the final assignment.
There will probably be a topic that is more interesting, maybe for some people than the others, so maybe there will be.
Give me your preferences, or give me at least a team you'd like to be with, if you have friends you want to work with, and I'll make the final assignments if there's a lot of overlap. All right. So I also need to take names of but who's here. So I'll come down and come to me one by one.